Welcome to Chapter 8 of this book. Chapter 8 is focused on the matrix inverse, which is an important concept that will really allow you to progress to advanced linear algebra and almost any linear algebra application. Now, as you learned in this chapter, not every matrix has an inverse. For a matrix to have a full inverse, it needs to be square and it needs to be full rank. And a matrix that is square and full rank has an inverse, but it has exactly one inverse. So when the matrix inverse exists, it is unique. And there are several implications of the uniqueness of the matrix inverse, one of which is that the inverse of the inverse is the original matrix. In other words, the inverse of A inverse is the matrix A itself. And this is analogous to, it's similar to, the reciprocal of a fraction is the original number. So imagine A here is a number like the number 7. You can reciprocate the number 7 to get 1 over 7, or 1/7. And you can reciprocate that again. So 1 divided by 1/7 is the number 7. Okay, so this exercise is conceptually important, but pretty straightforward to implement in code. We just want to create an invertible matrix, invert it, and then invert the inverse. And here you see that in code. So we have some random matrix, n by n, and as I mentioned elsewhere in the book, especially when these are floating point random numbers, this is basically guaranteed to be a full rank matrix. So here we take the inverse of that matrix, I call this AI, and here we take the inverse of the matrix inverse, which is AII, so the matrix inverse inverse, and then we compute the difference between the matrix, the original matrix, and its double inverse, so the inverse of the inverse. And some, maybe there's going to be some little tiny rounding errors here and there, but we expect these two matrices to be equal to each other, which means we get a matrix of all zeros.